So the course of differential equations, lecture number 1, Laplace Transform. This is the method of solving linear differential equation with constant coefficients like this. So it is written here. A(n) A0 are constants, such that A(n) is not 0. F of x is a given function. And we're looking for the unknown function y under initial conditions. So we are given also initial conditions. y0, y prime of 0, and so on, yn minus 1 of 0. So these are some constants. They are given in advance, not the derivatives of constants, but they are given constants, right? So, but at the second part of our lecture, we will discuss the method of solving these differential equations by the method of Laplace transform. But now we will need some definitions, theorems, and some preliminary facts to construct, to develop this theory, right? And we will start with the definition of the Laplace transform. I will use this part of the blackboard. So definition, we will start with the definition of Laplace transform. So Laplace transform of a function is defined via an improper integral, and so we will repeat the notion of an improper integral. So suppose f of x is defined on the integral from 0 to plus infinity, and we will need the improper integral from 0 to positive infinity f of x dx. So to introduce this integral, we will need the requirement that f of x is Riemann integrable. On epsilon b. So there are two singularities near 0 and at infinity. And in this case, the improper integral is defined as the limit as epsilon approaches 0 from the right and b, b approaches infinity, or plus 0, so let it be plus 0. The integral from epsilon to b f of x dx. So if this limit exists and finite, say equal to L, then this improper integral is called convergent, to be convergent, or we will say that it exists or it is convergent. Otherwise, it is called divergent. Well, and we will start with the theorem. So let's consider the improper integral of the form e raised to the power sx f of x dx. Let's discuss this integral. Theorem 1 claims that if this integral is convergent for some value of s, which is equal to s0, for some value of s equals to s0, then it converges for every s which is greater than x s0. So we will need this theorem. Let's discuss it. So it is not difficult to prove this theorem. So, but we should remind some theorems from calculus, right? The question is, so proof. Let's discuss the proof. How can we prove this theorem? Right? Which tests can we use in proving these theorems? Do you remember any tests for checking whether the integral is convergent or divergent, or so how can we prove it? Do you know? Do you remember any tests for convergence of Cauchy. So, but I think it doesn't work here. It is difficult to apply it. So do you remember some other tests? Okay, there are improper integrals of non-negative functions, right? So there are several. There are two cases maybe. The integrand may change sign or preserve sign, right? It may be non-negative or it may change sign. Is this function of constant sign or not? Do you know? So f of x is an arbitrary function. So so we know nothing about f of x. It may change sign, right? So we can't use maybe comparison theorems. It's comparison test, right, for positive functions. Okay, but what about functions that change sign? Do you remember theorems about the product? So what about the convergence of product of functions? From convergent, then f of x, g of x will be convergent. So I think maybe you mean the following. So from maybe let it be from 0 to infinity, as in our case. So the first so the first requirement is that the function so we have two singularities, right? Maybe 0 and infinity usually. Let's maybe to simplify our reasoning. Let's consider the singularity. Let's consider only infinity, right, as a singular point. But generally, we can cut this integral. So we should represent this as the sum from 0 to 1, for example, f times g dx plus 1 to infinity f times g dx, and consider the convergence of these two integrals separately, right? But let's consider one of them, say this one, right? This integral. Let's discuss the second integral. Okay, so we know that if f the just a moment, a primitive or antiderivative f of x, which is equal to the integral from 1 to x to, let it be to, so let it be y, for example, f of x dx is bounded, right? Bounded. Then, so, and what about g? If g of x is monotone and converges to 0, right? That tends to 0 as x approaches infinity. Then this integral f times g dx this integral converges, right? The same is true for this integral, right? For the second singularity. What is the name of this statement? Do you know? Do you remember? The name of this statement? So this is the Dirichlet test. And we can use it. In our case, let's try to use it. So first, we need to check that the antiderivative is bounded. The antiderivative of what? So we consider, so let it be from 1 to infinity, maybe, this is the second part of the integral, e to, so we know that this integral is convergent for some value of s0. Okay. Let's first let's start with the following. I will rewrite our integral, this integral, in the following form. Let it be e. So I multiply and divide. So I will multiply and divide by s0x times e to minus s0x times s to minus sx times c f of x dx. Okay, well, and it can be rewritten as the integral from 1 to infinity e to the power s0 minus s times x times e to the power minus s0x f of x dx. And we know that the integral, so this integral, right, this is convergent by the hypothesis of our theorem, right? This part is convergent, right? This is convergent, and this is a monotone function which approaches 0 as x approaches infinity. Why this approaches 0? So why e to the power s0 minus sx approaches, so monotone and approaches 0, tends to 0. Why is it true? Because the power, so s is greater than s0, so the power is negative. And x approaches positive infinity. So this power approaches negative infinity, and so e to this raised to this power approaches 0 as x approaches positive infinity. So we can use the Dirichlet test to prove this theorem. But maybe, so I don't want to get in detailed consideration of this theorem, because we should move further. We will use this theorem in our, so for constructing the Laplace, for defining the Laplace transform. And so this theorem is from calculus, and I don't want deeper consideration of this theorem. Okay, so we know that if this integral is convergent for some value of s0, then it converges for every s greater than s0, right? We will use this, and we will introduce the notion of the Laplace transform. We will define Laplace transform using this fact. Okay, so this integral is called the Laplace transform for the function f lowercase f of x if it converges for some value of s, right? So this will be the definition. I don't want to rewrite this formula. So this is called the Laplace transform of the function f if the integral on the left converges, if the integral for some value of s. This will be called the Laplace transform. Okay. And now we will need, in what follows, we will use Laplace transforms of some functions, and we will consider an example. It will be here. We will try to find the Laplace transform of the function 1. So this means that f of x is equal to 1. And we will consider x so it is given on the interval from 0 to infinity, s is greater than or equal to 0. And we will try to find the Laplace transform of this function. Let's do it. F of 1, by definition, is equal to the integral from 0 to positive infinity, e to the power of minus sx multiplied by the function, so by 1 dx. So we need to compute this. It is equal to minus 1 over s e to the power minus sx from 0 to infinity. This is improper integral, but so both limits are considered as limit of this, right? So if x approaches positive infinity, if x approaches positive infinity and if s is greater than 0, then this approaches 0. And so if we substitute the upper bound into the function, we will get 0, right? Plus, if we change the sign, 1 over s, and on substituting 0 in the argument, we will get e raised to the power of 0, and it is 1. So it will be plus 1 over s. And the answer is 1 over s, where s is greater than 0. Greater than 0. Okay, and the second example, let's find the Laplace transform of the function e to the power ax. Okay, it is equal to, so by definition, it is equal to the integral from 0 to positive infinity, e to the power minus sx times e to the power ax dx is the integral from 0 to infinity e to a minus sx dx. It is 1 over a minus s e to the power a minus sx from 0 to infinity. Now we are trying to substitute positive infinity, and we can do this if s is greater than a. S should be greater than a. And then this will approach 0, so 0 minus, or we can instead change the sign in the denominator, so plus 1 over s minus a. Okay, so this is the answer to the second problem, right? The Laplace transform of the function e to the power ax is equal to 1 over s minus a if s is greater than a, right? Now we will need properties of Laplace transform. We will discuss properties of Laplace transform. Okay, so, and the most important property is the linearity of the separator. Linearity. So it is theorem number 2. So given two functions, f1 and f2, if L of f1 is defined, so this means that it is convergent, right? Is defined for some s for s greater than s1, for all values of s that are greater than s1, and L of f2 is defined for s greater than s2, then let's consider the linear combination of these functions. So first, the first statement is, it is defined for, what is your opinion, for which values of s is this function defined? Is defined for so I think both should be defined. So it follows from part 2. If they are both defined, then we can state their linearity is equal to C1 L of F1 plus C2 L of F2. This formula follows from the linearity of the integration, of the integral, right? So since the integral is linear, so if we multiply the linear combination of functions by e to the power minus sx and integrate, so we may use the linearity of the integral. And so we can see that both this and this should be defined, both terms should be defined, both objects. And so it is defined for s which is greater than maximum of s1 and s2. Okay, this theorem is, so the proof is trivial, right? It follows from the linearity of the integral and from theorem 1, right? So proof from theorem 1 and linearity of the integral. From the linearity of the integral. Well, okay, and we will need the inverse Laplace transform. Let's speak about the inverse Laplace transform. Inverse Laplace transform. I think I will use this part. Inverse Laplace transform. for convenience, I will rewrite the definition of the Laplace transform. So L of f is defined as the integral from 0 to infinity of the function f e to the power minus sx f of x dx. If it is convergent, so for s greater than s0. If this integral is convergent for some value of s0. Okay. And before the definition, we need the following theorem, which we will state without proof. Right? We have no time to prove it. So the following theorem. So the first part is as usual trivial. So if if f1 of x and f2 of x are both continuous functions, and just a moment, f1 of x equals f2 of x for, let it be x greater than 0. Then their Laplace transforms are the same. So this is of course trivial, but the inverse, the second part is not so trivial. So conversely, if we know that f1 and f2 are continuous, and if L of f1 equals L of f2 for s which is greater than s0, then I claim that f1 equals identically f2 for all values of x that are greater than or equal to 0. So given these functions are continuous, if the Laplace transforms of these functions are the same, then the functions coincide identically. Okay, so we will omit this, the proof of this theorem, but I'd like to discuss it. So my question is it important that we are given that f1 and f2 are continuous? So if we, for example, if we refuse this statement, if we remove this statement that f1 and f2 are continuous, would it be true? Would we claim that if the Laplace transforms of two arbitrary functions are the same, then the functions are the same? Okay, so what is your opinion? Is it true or false? False, right? Okay, because if we consider two functions that differ at just one point, right? So, for example, we may consider f1 to be continuous and f2 is the same as f1, but we will change f1 just at one point, right? Then the integral will not change, right? And the Laplace transforms of such functions will be the same, but the functions are different. So this is a necessary condition, and it is important that f1 and f2 are continuous functions. They must be continuous. And for the continuous function, so we can see the uniqueness of the function. So it follows from this theorem that if we know the function L of f, then we can recover a continuous function, right, from its image, from its Laplace transform. And this inverse function is called the inverse Laplace transform. So if f is continuous, and if L of f is equal to f of s, this is another argument here. Then f is called inverse Laplace transform of f of s, inverse Laplace transform. For the inverse Laplace transform, the same property of linearity is also valid, and I will write it here. So the linearity of direct Laplace transform, and theorem number 4, the linearity, I claim the linearity of the inverse Laplace transform. So that is, if C1 and C2 are constants, then L inverse of C1 F1 plus C2 F2 is equal to C1 L inverse of F1 plus C2 L inverse of F2. And this can be derived from the linearity of the direct Laplace transform. So I don't want to pay time to proving this theorem, right? Because now we should move back to our main goal for today, right? So we should study how to solve the linear differential equations by the method of Laplace transform, right? Okay, so let's turn back to our equation, and let's apply Laplace transform to both parts of this equation. So this is our equation. Let's apply Laplace transform to both parts of this equation and use the linearity of the Laplace transform, and we will get the following: an times L of the nth derivative of y plus an minus 1 times L of y, yn minus 1 plus plus a1 times L of y prime plus a0 times L of y equals L of f. Right, and now our goal is to so discover the method of reducing the Laplace transforms of derivatives of a function to the Laplace transforms of a function. So it is possible, so there exists a simple formula that relates L of y to k, yk, and L of y. So our goal is to relate these two functions. So this function, this Laplace transform can be it can be represented through the function L of y in terms of L of y. To obtain this formula, we will make an additional assumption. Okay, so let y be n times differential function. So on the interval from 0 to infinity. And the additional assumption would be, so we will claim that the limit of e to the power minus sx times yk of x as x approaches infinity, positive infinity, is 0 for any k from 1 to -1, from 0. If the derivative of order 0 means is the same as the function itself, right? Right. So it may be so the function itself and all the derivatives of order from 1 to n-1. It should be read as follows, right? So suppose this is true. Then let it be theorem 5. Theorem 5. In that case, we claim that L of the nth derivative of y is equal to s to the power n times L of y, right, minus something. And now we will need these initial conditions. Initial conditions will be included. So minus yn minus 1 of 0 plus s times yn minus 2 of 0 plus dot 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 plus sn minus 2 y prime of 0 plus sn minus 1 times y of 0. Okay, now we will prove this. So it will be by induction. On n. So the base step n equals 1. Let's substitute n equals 1. And let's try to find L of y prime. So it will be equal to the integral from 0 to infinity e to the power minus sx y prime of x dx. Okay, and how should we proceed further? So what shall we do to find this integral? What is your opinion? We should reduce this integral to the integral without derivative. So to the integral of y, not the derivative of y. How it can be done? Do you know the methods of reducing this integral to the integral which do not involve the derivative? What are the methods of integration? Do you know? By parts, right? Integration by parts. Let's use the integration by parts. So we will rewrite this as the integral from 0 to infinity e to the power minus sx d y of x. And by integration by parts, it is equal to e to the power minus sx y of x from 0 to infinity, then minus, then we should differentiate this function. The derivative of this function will be minus s, so it will be minus s e to the power minus sx, right, times y of x dx, right, by the formula of integration by parts. Clear? Then let's substitute the upper limit, infinity, into this function. But look at the assumption. So this limit is equal to 0. It was assumed. And so we will use this condition, right, for the function itself. If k equals 0, then this means the function itself, right? So on substituting infinity, we will get 0 minus, and the lower limit, 0. This will be a y of 0, and this is 1, right? So we will get minus y of 0. Okay, do you agree? So on substituting infinity, we will get 0 here. And on substituting 0, we will get minus y of 0, because this will be 1. The power is 0, so it is 1 multiplied by y of 0, so minus y of 0, right? And we will simplify this, so minus and minus, so double minus will give us plus, right? Plus. So s is a constant here. It can be moved through the integral sign, plus s, the integral from 0 to infinity, e to the power minus sx y of x dx. But this is the Laplace transform of the function y. So we can see, so from the first step, we can see that L of y prime equals s multiplied by L of y minus y of 0, right? So this is proved. Okay, you can see that this is a particular case of this general formula. Let's check this. So if n is equal to 1, then this is 1, right? So this is so they are the same for n equals 1. Then if n equals 1, then this is just y of 0. It's y of 0, and this, so this part vanishes, right? Because n is 1, and so the negative, what is negative derivative, right? Right, so the first part is proved, and now we should move on to the inductive step. So this was this base step, and then the inductive step. the inductive step. By the inductive step, we assume that this formula is true for n equals k, and we will try to prove that if this is true, then the formula is true for n equals k plus 1. Right? So this is the inductive step. So suppose L of y k is equal to s times L of y minus yk minus 1 of 0 plus s yk minus 2 of 0 plus dot 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 plus s k minus 1 times y of 0. And let's try to find L of y k plus 1. By definition, it is the integral from 0 to infinity e to the power minus sx y k plus 1 dx. We will use the integration by parts again. We will move y to the differential sign, and this will be the integral from 0 to infinity e to the power minus sx dyk. Next, apply the formula minus sx y to the power k from 0 to infinity minus, so it would be plus, so the same, it would be the same from 0 to infinity e minus sx yk dx, and on substituting we will get so infinity. So if we substitute infinity, this approaches 0 by our assumption, this one, and so it would be minus yk of 0 plus s times L of yk, and next we use the hypothesis. So we assumed that the formula is true for n equals k, so this formula is true, and we need to substitute this formula here, right? Let's substitute it. So L of yk is this. We must multiply by s, and we will get s to the power k plus 1. L of y minus, and we need to multiply all this expression by s, right? And add this, and we will get minus. So this should be multiplied by s, because here we multiply by s, so this also should be multiplied by s. And this is minus, so minus yk of 0 minus s times yk minus 1 of 0, so plus, plus. Okay, so it would be sk times y of 0. Okay, so this formula is proved. Okay, so now, let's apply the Laplace transform. Let's apply this theorem to this differential equation, and let's try to write the resulting formula. The resulting formula would be, so an multiplied by the Laplace transform of yn. It would be an times the Laplace transform of the nth derivative of y can be calculated using this formula. So we can see that an is multiplied by s to n, right? I am applying this formula. It would be s to n times L of y minus this expression n minus 1 of 0 Okay, so this is just the first part. Next would be plus an minus 1 and the same s to the power n minus 1 L of y minus y n minus 2 of 0 sy n minus 3 of 0 Sn minus 2 y of 0, right? And the last would be a0 times L of y equals L of f. Now I want to rearrange, so regroup the terms contained in this formula. So I want to gather, I want to gather the terms with L of y. So we know, so these are numbers. This is a polynomial in S, right? As you can see, this is a polynomial in S. So this is a constant. Y of n minus 2 of 0 is also a constant, right? These constants are given, and this is a polynomial in S. But our goal is to find L of y. So what is the method of Laplace transform? Okay, I'd like to describe it shortly, and in what follows we will develop the so the method more so deeper, right? But now, so in short, the Laplace transform method transforms, as the name suggests, it transforms, it solves the differential equation via transformation of our functions to other functions using the integral. And by this transformation, after this transformation, the differential equation is transformed to the algebraic equation. Algebraic equation in L of y. And after this, we will construct the table of Laplace transforms, so likewise, just a moment. Okay, so as we have the integral tables, right? We can create the tables for Laplace transforms, and we will obtain the Laplace transforms and inverse Laplace transforms from the table. So we will create it at the end of the lecture, right? But now let's finish this construction. So L of y is multiplied by what? What is the coefficient of L of y? Look here, an is multiplied by Sn. So an times Sn plus an minus 1 times Sn minus 1 plus dot 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 plus a1s plus a0. So you can see that this is just the characteristic equation. It looks like the characteristic equation for this homogeneous differential equation, right? So this polynomial can be obtained as follows. We should take the homogeneous part of the differential equation and replace the derivatives by the powers of s, right? And so we will create this polynomial. L of y is multiplied by this polynomial minus, and then we should subtract something. Okay, so what would it be? Usually we start with y0, so y0 is multiplied by, so an times Sn minus 1. So this is the coefficient of y0. The first coefficient is an multiplied by s to n minus 1. Then plus an minus 1 times s to n minus 2. Look at this polynomial. This polynomial can be obtained from the preceding one by decreasing the power of s by 1, right? And removing the last term. And we will get this times y of 0. So minus. And if we proceed in the similar way, we will get an times s to n minus 1 plus dot plus, and we will end with a2 times y prime 0 minus, and the last would be an times y n minus 1 of 0 equals L of f. So we get several polynomials. So this is a polynomial. After this, the method is to solve for L of y. So method and using the table for Laplace transforms, if we know the the function L of y, we can recover the function y from this table. Well, and now our goal is to create the table of Laplace transforms. Okay, so we know the Laplace transforms of two functions. Right. So if f is equal to 1, then the Laplace transform is equal to 1 over s. S is greater than 0. If f is equal to e to the power a x, then the Laplace transform would be 1 over s minus a, and s is greater than a. This was obtained. This was obtained in the example number 1. And now I want to continue this construction. But maybe I have forgotten to give a simple example of solving some simple differential equation. Maybe it is also important. So next we will continue constructing this table. But first, let's consider an example. Example number 2. We will solve some simple differential equation. I will show how this works, how this method works, using some simple example. Okay, now we will try to solve this differential equation. Plus 2y equals 0. If y of 0 equals 2. We will try to solve this. Okay. By the formula written there, we can see that the polynomial, the characteristic polynomial, that is s plus 2, is multiplied by L of y minus, okay, what about this part? We have only y of 0, and we should reduce the power of this polynomial and remove 2. So 1 times y of 0 right? So I will rewrite this as s plus 2 times L of y minus 2 equals 0. Then L of y equals 2 over s plus 2. Okay. And now our goal is to guess the original function. Who knows how to find y? What is y? If the Laplace transform is 2 over s plus 2, what is y? Okay, so look at that part of the board. It looks like, so s plus 2 in the denominator means that we need e, right? E to the power of what? So s minus 2, right?
But this is in the form of 1.
Right, but we have 2, and there we have 1. But we know the linearity of the Laplace transform, right? So it is 2 multiplied by e to the power minus 2x. Well, so this is the answer to our differential equation. We may check. Let's check. Y prime is equal to minus 4e to the power minus 2x. Right? Then if we multiply this by 2 and add to this function, we will get 0 as required. And the initial condition, y of 0 equals 2, y of 0 equals just 2, right? So magic. Right. Well, what is the advantage of the method of Laplace transform? So the advantage is it works for the initial value problem, right? So to apply the Laplace transform method, we need the initial values, right? It doesn't work without initial values. And we get the answer to the initial value problem immediately, right, from the given initial conditions. So without the method of Laplace transform, if we use the method studied in the previous year, right? So in spring we solved these problems, these differential equations, and the solution includes two steps. First, we are trying to solve this so first step is solving the homogeneous differential equation. Then the particular solution of the non-homogeneous differential equation. Then we should find the sum of this, right? The general solution of the homogeneous equation plus a particular solution of a non-homogeneous equation. And then, after all, we should find the constants involved in the general equation, general solution, using these initial conditions. So sometimes it takes a long time to perform all the steps, right? But now, by the method of Laplace transform, we use simultaneously the differential equation and the initial conditions. And we get the answer to the initial value problem immediately, right? But to do this, we need to construct the table of Laplace transforms, and we know the Laplace transforms of these two functions. And at the end of this lecture, so we have 5 minutes to finish our lecture. So I will start, and we will continue during this seminar, and after this we will try to solve problems, right? This will be the plan. And so at the end of the lecture, I will try to find L of xn. Let's do this. L of xn. This is the integral from 0 to infinity of xn, so of e to the power minus sx just maybe it's not it's better not to start with this, because so we need some theorem. Maybe it's better to use some theorem. Let's not do this, but let's find the Laplace transform of sine or cosine. For example, sine ax, maybe. From 0 to infinity, e to the minus sx, sine ax dx. I want to find this integral. What shall I do? Do you remember how to find this? Using the integration by parts. Integration by parts. So let's move, let's move e under the, it doesn't matter, but I will do this. It would be sine ax times d of e to minus sx and minus 1 over s here. E to the power minus sx from 0 to infinity plus and so multiplied by a. So if x approaches infinity, this approaches 0. And if x equals 0, this is 0. So this is 0 minus 0. If x approaches infinity, then this approaches 0. If x is equal to 0, then sine ax is 0. Right? So this vanishes. Well, and we are left with this. And we will again apply the formula for differential for integration by parts, and this will be minus a over s squared, the integral from 0 to infinity cos ax d to the power minus sx by parts. And differentiate, so it would be change the sign, so it would be minus. So minus 1, 2, and minus from differential from the so the derivative of course is minus sign, so we will get minus a over a squared from 0 to infinity. Be a squared sine ax e to minus sx dx. Well, substitute the limits of integration into the formula. On substituting positive infinity, we will get 0. And on substituting 0, here we will get 1. Cos 0 is 1. Minus a, so minus a over s squared. And minus a squared s squared times, and if we call this integral I, so I, we will get the equation equals minus a over s squared minus a squared over a squared times I. And to find the integral, we need to solve this equation. Multiply all the parts by s squared and move this term to the left. We will get s squared plus a squared times I equals minus a. Right, but it should be plus a, I think. Why? So minus, it's plus because we should subtract. If we substitute 0, we will get minus, but it should be subtracting, so plus. So it would be a, from which we have I equals, the integral equals a over s squared plus a squared. So now we have the following. So it was sine. It is a over s squared plus a squared. We stop here. Now we will have a break. And on the seminar, we will continue constructing the table. And we will try to solve some more complicated tasks.